Good morning all. Today we're going to take a look at this Lika electronic absolute encoder, and it is part number AM69/100 PET.2.5:1 2.5 to 1. Now you can see that this is an amazing device. I'm going to rotate the shaft of the absolute encoder and you can see the gearing that is required to rotate this wheel, this code wheel, this code wheel, and this code wheel. Now we can see the code wheel of this device, but the code wheels of the second and third are inside this assembly. But you can see the gears. It's amazing. This one turns the fastest. This one turns at a slower rate. And this one right here turns at the slowest rate. The DB25 connector, we apply a voltage to 2 pins of this connector, and the outputs, there's 18 outputs of this. They're open collector NPN. We're going to put this encoder on my encoder tester, and we're going to try to determine if there's anything wrong. If there is something wrong with this encoder, I think we're just going to leave it as is, because to take this apart and put it back together, properly timed, the gears between this code wheel and this code wheel and this code wheel and the shaft, to get this back together properly timed would be near impossible. Now, one solution, if you absolutely had to take this apart, is to take a putty and jam the gearing in one position, like take the putty and jam these gears with the putty, jam these gears with the putty so that they don't move, and then jam these gears with the putty and disassemble, trying not to move the gearing. Look for the problem if you can find it, and then reassemble it, trying not to move these gears, because the gears are timed together. It would be a bear. That would be a grizzly bear trying to take this apart and put it back together properly timed. Whew. I don't know if I'd even try it. Let's go put this on the tester. Now the cooling fans on my tester, they're a little bit loud. So here is the cooling fan that cools the stepper motor, and here's a cooling fan that cools the MOSFETs that run the stepper motor, that drive the stepper motor, and they also cool the input resistors of the optocoupler, because they can get pretty warm, especially if I have the encoder voltage set to 24. Let's loosen up the bracket here. adjust the stepper motor closer to the mounting, the encoder mount, or farther away from the encoder mount. Got some O-rings on the shaft of the stepper motor that mate to the step-down wheel, Someday I might, I don't know when, if ever, but someday I might install a gearbox instead of using the wheels, but don't fall off. It's so hard to get on here. Come on, don't fall off. There you go. All right, we'll tighten everybody down. We're going to connect our interface cable. There we go. Just tighten up the bolts here. Tighten up the bolts of the stepper motor mount. See how that goes. There's some wobble to it. The wobble comes from not having the cylindrical housing on the encoder, but we'll see how that goes. Let's start up our program. Set this to 12 volts DC. Odd. Well, we're rotating. Let's go to 24 volts. Well now, look at that. Let me get you closer to the screen. Clear this out. And we are rotating, but the values are not changing on the screen. Turn the motor power on to the stepper motor by clicking on this button right here. We can turn it on and off. Let's go up here and we'll start the test. You see that? Now the stepper motor is rotating the absolute encoder, but these values are not changing. So either the absolute encoder voltage, there's a 5-volt regulator in there. Now either that's not working and applying DC voltage to the logic of the absolute encoder, or the code wheels are not working. The IR transmitters and the IR receivers. I can see the gears rotating. So the code wheels should be rotating. Very strange. Okay. Well, there's our problem. We'll have to figure that out. Let me put a good absolute encoder on there, and you can see the different tests that we can perform using my absolute encoder tester. And we're stopped. The stepper motor stopped rotating. I'm going to set that voltage back to 12. And I can smell something got hot. Something got hot in here. There's our problem. Whatever got hot. You smell burnt semiconductor. Whatever part got hot is why this absolute encoder is not working. Well, maybe it'll be an easy fix. Well, let me put a good encoder on there and we'll take a look at how the program works. We click on motor power. That applies the power to run the stepper motor. I got an on-off switch here for the stepper motor power because sometimes I just want to rotate the encoder by hand and I don't need the stepper motor, so I can turn it on and off. Let's go up here. Now you see that? Stepper motor's rotating that encoder, and we can see the data bits from the encoder, the outputs, changing. Now this encoder only has 18 outputs, so this column right here, these 4 bits, and these 2 bits right here are not used. Let's stop the test. Now I have previously saved the data from that encoder, and we can go down here, we can click on Save Encoder, click Yes, and it will pull the data out and save it to the hard drive. Then we can come back here and compare the data that we previously saved to the encoder. So let's click Yes and go up here. The C drive, encoder directory, and this part number encoder is AM609. Open the file. Okay, it says search the PC disk file for the current position of the absolute encoder. Click OK to start the PC disk file search, or click cancel to exit the comparison test. So we're going to click OK. Down here it says retrieving number of disk file records. We have to know how long, how many files are in there, so we can compare from the beginning, starting at F29FA hexadecimal, and the tester will rotate the encoder and look at the different hexadecimal values to see if they're the same. If they're same, we go to the next one. If they're not, we'll kick up an error. So it says found current absolute encoder position in the PC disk file. Click OK to start motor and comparison test. Click cancel to exit comparison test. So here we go. We have a bar graph right here when it reaches the end, and we have about 100,000 encoder numeric count here. That will be the complete comparison test. Now this encoder takes about 12-13 minutes to complete the test. So we'll just let this run out. We can watch it as we go along. I'm gonna go get a cup of coffee while y'all's watching. Back with my coffee. Y'all go get a coffee or tea? So up here, these are the actual bits that are retrieved from my encoder tester and processed by the computer, the PC tower over there. Now, I take the bits, and through software conversion, this column shows gray code. So it takes these bits and through a software conversion routine displays the gray code. This row right here shows the decimal value of these bits in this column right here. This column is the hexadecimal conversion of these bits. And the file that was saved saves the hexadecimal conversion. And that's what's being compared right now. So far, no errors have popped up. So the values in the hard drive file compared to the actual values of the encoder over there are working. They're being compared to each other, and they're equal so far. Now down here, this column shows the Petherick code conversion. I can click these check boxes right here to turn off the conversion. It bypasses the conversion. If you wanted to speed up the process, you could check these boxes right here, and they wouldn't be converted. These bits wouldn't be converted. So far, we have a count of 40,000. We're almost halfway there. Here, we've reached halfway. We have a count of 50,000. See that these bits down here, these 8 data bits, they change at a faster rate than these bits up here and these bits over here. These aren't used, so they have dashes in there. There's no data bits in that encoder for this column right here. And these 2 bits, they'll never change also. because there's only 18 data bits at the output of that absolute encoder. So these 6 bits right here will never change. So these would be the first code wheel. This would be the second code wheel, and this would be the third code wheel. Where are we at now? 65,000. 66,000. It moves along at a pretty good clip, doesn't it? Put the hardware together back in 2001, thereabouts, and I've been working on the software ever since. there's tiny little bugs in the software that are elusive, and easy fixes. I don't know, gotten too old to go in there and correct the minor bugs. At a certain point, at a certain age, you get to just leave stuff alone. Oh well, they're just minor nuisances actually, not preventing the program or the hardware from working. Where are we at? There's 80,000. 80,000. 19,000 to go. 18,000 to go. We are almost there. Now when it gets to the end, the stepper motor will stop rotating, and a message box will ask us to click on show failures, and it will show warnings or failures or whatnot in another panel that pops up over here when we click on that show failures button. $87,000. $88,000. We're getting there. You can see our bar graphs almost all the way over to the completed side. Get another sip of my coffee while we're sitting here watching this. Oh yeah, that's good coffee. We're at 92,000. 8,000 to go. $5,000. 96,000. 97,000. 3,000 to go. We are very close. $99,000. There we're at the end. Finish comparison test. Click Show Failures to view encoder failures. Alright. We're going to click on Show Failures. And up here, in the Show Failures box, this little panel right here says No Failures. We had a successful comparison. And it took 1204 to 1218. Now let's perform another test. This one is really cool. We can do a bit toggle test. And what that will do, down here in the bottom, this little panel right here will show zeros and ones for the bits that have toggled from either 0 to 1 or 1 to 0, indicating that that bit functioned. So for instance, if this bit right here went from, let me get my pencil and show you. Hold on, let me go get my pencil. There we are. There, come here, pencil. Whoops, bump the camera. So if this bit right here went from 0 to 1, we would have a 1 down here. If this bit right here went from 1 to 0, that bit would show a 1. If this bit went from 0 to 1, that bit down here would show a 1. And we'll rotate through all of the 100 pulse count of that encoder, and in the end it'll stop and show us which bits function properly. If we have one bit that did not change, that bit would be bad. Now, we have to ignore these 6 bits over here. They're going to show 0 because they don't change. Let me get closer to the bottom of the screen there, and we'll look at this down here where the bits are going to show up as these bits. I'm going to select yes for bit toggle test. And the message says, click OK to start test, or click cancel to exit test. I'm going to click OK. And you can see down here, these first 8 bits, they've already passed. Those bits toggled. They went from either 0 to 1 or 1 to 0. These bits over here have toggled. This one here is toggled. Oh, you can see that one just went to a 1, indicating that that bit toggled. We can ignore these 4 bits and these 2 bits right here because they don't exist in that encoder. We'll sit here and watch those bits change as we go from 0 to 100,000 pulse count. Where are we at now? We're almost at 10,000. 3 more bits need to change state. This one, and this one. Now if they change state before we reach 100,000 count, we can stop the test by hitting the stop test button. 2 more bits need to change. I can still smell that burnt encoder. Oh, that poor encoder. We're gonna have to fix that. Imagine rotating that encoder by hand and trying to check these bits to see if they toggle. Or to do a comparison. It would be near impossible without some way of rotating that encoder with a motor and processing the data bits. It would oh man, just to rotate this thing by hand would probably take you all day. Because you have to look at 18 outputs. Whew. I don't think I could do it. All right, just one more bit to change. Yeah, I don't think I could rotate that thing by hand and look at 18 outputs simultaneously. It would be impossible. Well, no, it wouldn't be impossible. It would just be impractical. By the time you get to the 18th bit, you'd be so wore out that you wouldn't even want to repair that encoder. Ah, jeez. I wonder how people used to do this before I made the tester. Alright, we're at 32,000 pulse count. There's 33,000. Ways to go before we make it to 100,000. Just one more data bit to go. It'll be a while before we see that bit flip. This one right here has not been tested yet. Oh, look at that. There it went. At 43,000 pulse count. The last bit flipped. I pointed right at it and it flipped. What's the chances of that happening? So, all 18 bits are properly changing from 1 to 0, 0 to 1. So, we could stop the test right now. And I think I'll do that since we know that all 18 data bits are working. That is the bit toggle test. Let me click the stop test button. There we go. Now what else can we do? we can go 1 revolution. I have a radio button. If I select yes for 1 revolution, it will rotate through 1 revolution and stop. The 1 revolution radio button right here, I'll point at it with my pencil, you can click yes and the encoder will rotate through 1 revolution. I'm not going to perform that test because we have already gone through 1 revolution a couple of times. So you click that radio button right there, you start test with this button up here, and the stepper motor and the program will rotate that absolute encoder through 1 revolution. It will count from numeric count here of 0 up to 100,000. Now it's looking at, this is the value down here that we started at. Let me point at that with my pencil. This hexadecimal code is where we started at, FCAA36. And the F part right there, that's your F. It's not actually used, but it's looking at CAA36. F's not existent in that encoder. And the first 2 bits, the most significant 2 bits right here are not used also. But this is where, when that encoder rotates all the way around, it's going to stop when we get back to this value right here, FCAA36. And that's in the hexadecimal column, or the hexadecimal row right here. Got to get another cup of coffee. I can't speak properly. Let's slow things down. I can click on these buttons over here and these buttons over here to slow the stepper motor down and speed it back up. Let's get slower here. Okay, you can actually see the least significant bits changing. These bits right here, you can actually see their values changing. Whereas before they were a blur. Let's go faster. Click on the faster button over here. All right. It's been a while since I've tested an absolute encoder. But you got to see how the program works. Let's take our burn up encoder, our burn up absolute encoder over here, and we'll try to figure out what happened to it. Why it's not putting out, why it's not working. If y'all has ever smelt a semiconductor that burn up, you know the smell I'm talking about. It's an acrid smell, acidic. It's a smell like no other. Let's go back over to the bench with that encoder and we'll take a look at it. The intensity of the burn smell is in this area right here. So I am going to remove these 3 screws, flip that plate down, and we'll see if we can possibly determine who was burned up. Whoops. Picked up a resistor with my magnetized bit. Now maybe we'll get lucky and we'll be able to see what is damaged. If not, we'll pull the meter out and use it to determine who is shorted or who is damaged. Here's a 5-volt regulator, part number L7805CV, SGS Thompson. Let's put our meter on that. Can you all see that okay? Red lead on ground. Oh yeah, look at that. Our 5-volt regulator, the input side is shorted. Now this 5-volt regulator, oh luckily the output side is not shorted. Ground to pin 3 of that regulator is 0.522. Pin 1, the input side to ground, get on there. We have a diode drop of 0.005 volts DC. We're going to have to change that regulator, and that should fix our absolute encoder. Phew, we lucked out on that one. Now, if it had shot through, there would have been nothing that we could have done about this, because there's just too many ICs on this board. Look, just on this interface board right here, we have 1, 2, 3, 4, 5 ICs, and on the back side there's I see 1 IC. Whew. And that's just here at the front end. Okay, well, we'll save that repair for another day. Oh, I'm choking up on that smell. Phew. That is bad. I don't know if y'all have ever smelled a burn-up semiconductor, but it is a smell that you just never forget. Okay, there we go. We'll change that IC out some other time, and then we'll put this back on the encoder tester and see what we get. We'll do the bit toggle test and the comparison test with my absolute encoder tester. There you go. Wasn't that fascinating? Have a good day, all. And we'll see you on the next one.